Hello and welcome. The topic of today's video is acceleration structures in ray tracing, real-time ray tracing. And this may seem a little obvious, but to start it off, I want to point out the motivation, the benefit of acceleration structures. So typically, if I have 10 spheres in my scene, then for every ray, 10 operations, 10 spheres must be tested. This is logical. That's the complexity curve of a single ray trace with regard to the number of spheres. So if we've got 16 spheres, then we are doing 16 ray trace operations. Now, in theory, if we are able to subdivide our space by some factor, like subdividing in twos or something, then the theoretical complexity would be log x. Now, this isn't quite that way because the number of spheres that we're testing is log x, but we've also got a few boxes, a few virtual boxes that we need to test, which adds a little bit onto that. But I just want to show how dramatic that difference is. So if we zoom in and we're looking at like 4 spheres, then for 4 spheres may not seem like such a big deal. But then as we go out, it makes a massive difference. So this is what we call sublinear. And again, it's probably not a pure log x, it would be some multiple of log x, but this is the fundamental curve difference. Now, where this gets even more extreme is if we start bouncing. So if, let's say we have 4 bounces, if we bounce a sphere ray once, then those n, each of the n rays must then be tested against all of the other n objects. So if we have 2 bounces, one bounce, so 2 traces, then we get that. And let's say we have 4 bounces. Well, then this is n to the power of 4, which, as you can see, the number of tests we need to perform massively increases. Now, it's probably not quite this bad because, again, a lot of the spheres will bounce off, a lot of the rays will bounce off a sphere, then hit the sky and terminate. But again, just for illustrative purposes, if we take this log x and dial it up to the power of 4, then it is still, it's growing faster, but it's still significantly performing significantly better than brute force ray tracing. So the whole purpose of this video is how do we design an algorithm which will perform better than brute force and run on the GPU. So as always, let's have a look at the brute force approach first. I would strongly recommend you open up the source code for this session, have a look at the start folder, and get familiar with this program if you're not familiar with it already. I know this is, stage 11 or something of my playlist, but it's still good to refresh ourselves because some things do change a little bit in between. But the program as it is at the moment, again, just give it a second or two to upscale. But we have we have 1,024 spheres uniformly distributed in some space. And we are adjusting, we've also got 4 samples anti-aliasing, which is why the edges look fuzzy, and 4 rebounds per sphere. And another reason the edges look fuzzy, of course, is that the resolution depends on the frame rate. So trying to maintain 60 frames per second, give or take 10 frames, it has to downsample quite a bit. And you can see this makes it look particularly ugly. So the purpose of today's session is to see if we can improve the performance so that we get this thing looking not like a dog's breakfast, if you catch my drift. Okay, so there it is. Now I'll just insert a video briefly explaining the concept of the algorithm that we're going to implement. Okay, so let's say that we have a tree structure of some sort where a circle represents an internal node and a square represents an external node. So something which has primitives in it which we can go ahead and render. Okay, so this is the bounding volume hierarchy which we want to render. The issue is, how do we write an algorithm which traverses this and can potentially prune parts off the tree, so not search certain parts, and yet does not use recursion? The thing is, GPUs, they hate recursion. So it turns out the solution is pretty straightforward. What I'll do first of all is I'll just label each node with an index, and this will be in a depth first search manner. So we go down here and then we look at the next child, something like that. Now each node is also going to store the index of the node which we should check based on the result of each thing. So we'll put green and we'll say, where should we go if we trace node 0 and we intersect it? Okay, well then let's keep going. Let's search node 1. Then we hit node 1. If we intersect that successfully, where should we search next? Let's search node 2. Okay, now after we hit node 2, we're not done because we could have other things. So we then search node 3. If node 3 has been hit, we search node 4. If node 4 has been hit, we search node 5. If node 5 has been hit, everything here has been hit successfully, we then look at the next child which hasn't been searched and continue the process on and on and on. Okay. So, in the worst possible scenario, we are somehow hitting everything. This is, I don't know, imagine that we're looking down a line of spheres and they are all in our range of visibility. Okay, so this is where the interesting bit comes in. These have all got indices. Now let's say that we have a index which represents total failure. Okay, so we'll give it a nice sensible value like -1. Okay, so if we go to the root node and we shoot a ray at it and we miss, we'll then go to the failure state. And the failure state is just some state where the loop will just keep continuing on and on and on and just run its course without doing any extra computation. So see, if we shoot at the root node and then we fail, then we have effectively we skip searching the whole tree. Now, if we go to root node 1 and we fail, well, then we'll search node 6. And so this whole left half of the tree is skipped. Now, similarly, if we go to node 2 and we fail, then search node 3. If node 3 fails, well, then we're not going to search 4 and 5. We'll skip over to 6. So the way this construction goes is actually fairly straightforward. Okay, so for a success, if the node is internal, then the success node is its left child. If the node is external, then the success node is the right child of its parent. And we can see here, if the node is external and it is the right child, well then let's say that right child function is recursive. And we can do this on the CPU, by the way. We're constructing it ahead of time. So we go up to node 3, we say, hey, node 3, what's your right child? It says, it's you. So it looks at its parent and says, hey, I'm node 3, what's your right child? And node 1 says, it's you. Okay, so then you know what I mean. You know what I mean. So just for the sake of completeness, I'll finish off this tree. We can see here on node 6, if we've tried node 6 and that's failed, well then, nothing. We're done. And similarly, if we try node 10 and we fail, well then clearly we just didn't hit anything. That's okay. So with this data structure, as you can see, it's using skips without recursion to miss off whole sections of the tree. Okay, so we're going to do this in stages. It'll take a bit of time. Let's start with the shader side programming. So we'll head to our ray tracing shader and we'll add a new struct to represent a bounding box node. Now this is going to have a few things. First of all, we'll need two vec3s to represent the bounds, the minimum and maximum bounds of the box. And then we're going to reference each individual node by an index. And we're going to have two more integers. We're going to have a hit link and a miss link. And these will reference other bounding boxes, the indexes of other bounding boxes, if that makes sense. Now, as well as that, each node, if it is external, is going to have a bunch of spheres that it references. And we're going to have a table of all the IDs of the spheres, if that makes sense. So we're going to have a starting ID and then a count. Now the count is the number of spheres which is being referenced, and the ID offset is the location of the first sphere ID. So we're actually going to have a whole list of spheres which each of these nodes is going to be referencing. It's a little tricky. There's a level of indirection going on here. So for instance, let's say sphere number 3. If we know 3, then we can run our function and look and unpack, sphere number 3 and have its data. But then sphere number 3 may be held within multiple bounding boxes. And so that number 3 would show up multiple times in the sphere lookup table. So then we say, hey, node number 2, what are your spheres? And node number 2 says, I'm this chunk of memory in the sphere lookup table, and sphere number 3 just might happen to be in there, if that makes sense. We'll go more into it a little bit later. So we also go down to, where are we? These images, these textures, and we're going to have another 2. Binding number 2 is going to be the nodes, and then binding number 3 is, like we were saying before, that chunk of sphere data. So I'm going to call this the sphere lookup. So what else we got here? Sphere count and node count. Yep, that looks okay. So then we can go to the unpack functions. So here we have unpack sphere number 3, for instance, and I'm also going to make an unpack node and a lookup sphere index. And this is that indirection that I was talking about. So we say, hey, entry number 10 in our sphere lookup table, which sphere index is that referring to? And then it will look inside that data and read that out. We're also going to need a different hit function. We've got a hit function right now to check against a sphere. Now we'll need to make an axis-aligned bounding box function. Anyway, this is going to return true or false, indicating whether the box was hit. We're going to test array against a node. And we are also going to put in a nearest hit parameter. And the purpose of that is so that we can accurately reject boxes. Now, the tmin, the nearest hit parameter, is only set when we hit a sphere, because a sphere is a solid visible thing. If we hit a box, we do not update. So we don't need a render state in here. We don't update anything. Because just because we hit a box, that's not a guarantee that we have physically hit something. However, it is good to check whether the box, the virtual box that we're testing against, is further away than a sphere that we've already visibly hit, because that means we can reject that box and it speeds up the traversal quite a bit. Okay, so I think those are the function prototypes. Now we'll go down, we'll sort of take this from the lowest level back up to the highest level. Let's start with unpacking the node. So as with all things, I think it's a good idea just to write out the expected layout in memory, so we can see that we're going to use 3 pixels to store each node. And I just noticed we probably don't need these extra pixels. I'll have to, actually, you know what? Let's do that now. So we'll just go back to the engine. All right, select interpreter. We had an interpreter. What's wrong with this? Okay. So anyway, create resource memory, and then down here for the sphere. Oh, I've updated that already. Oh, okay. No problem. Yes, we are using 2 pixels for each sphere. Okay. Let's say that was fine. Okay, so we have this layout, and as you can see, we're probably going to need to read 3 pixels. So we can just... Actually, I'm going to grab all of this code and we'll just adjust it. Okay, so now we just have a lot of fun reading off from this layout. I'll just go ahead and fill this in. You can follow along if you like. Okay, so hopefully, as you can see, this is lining up with the memory layout we have up here. It's all looking good, although knowing me, I probably messed something up, but that's okay. It happens. We'll find out soon enough when we go to run this. There's a quick thing. Okay. So the next thing is we need this lookup sphere index. And this is actually quite a simple function. So as you can see, we just need 1 pixel, and we literally just need one thing. So we will go ahead and load up from the sphere lookup table. That's looking fine. And then we can pretty much do nothing. So we just return the first number, cast it to an integer. That is it. So again, what this looks like is it'll be a whole lot of numbers like 1, 2, 3, 7, 13, referencing specific spheres. And the results of this will later be used in the unpack sphere, which you'll see in a second. Let's go to the bounding box collision. So we'll close all of this down. Yeah, okay, I don't know. We're not really going to use this, but that's fine. We may as well start with something. Okay, so what we're doing here is we are finding the individual t parameters along each of the dimensions. So what that's saying is if we look along the ray's x direction, how far would that ray have to travel in the x direction until it hits the minimum corner? And this will be a different number to how far it has to travel in the y direction and how far it has to travel in the z direction. Now we can also take this and reverse it. We can say, okay, how far does it have to travel to hit the maximum corner? And this doesn't, depending on the orientation, the maximum corner might actually be closer than the minimum corner. So what we do is we take the actual minimum component-wise of the two and call that T1. That is the parameter to hit the nearer of the 3 dimensions. And we'll do the same thing with T2, get the actual maximum of those. And what that means is, say for instance, to hit the x-coordinate of the minimum is a smaller t value than to hit the x-coordinate of the maximum. Okay, well then the first component of T1 will be based on T min. But then it might happen that to hit the y-coordinate of the minimum is actually a larger value than to hit the y-coordinate of the maximum corner. Well, what this min function is going to do is it's going to select the y-coordinate of this T max as that is the smaller of the two. So in other words, we're just making sure that T1 has the smallest possible t values for each dimension, and T2 has the largest possible t values for each dimension. Then we sort of crunch those numbers together. So we want to get this down to a single float. And ironically, we're actually going to take the maximum of each of these. Because if you think about it, well, let's say it's 0.1 is the t distance to hit the x coordinate somewhere on the box, and 0.2 is the t distance to hit the y coordinate somewhere on the box. Well, in order for the ray to intersect, all dimensions must be matching. And so if you have a bunch of minimum t values, t parameters, the only thing that sequence can do is increase. You want to get the largest minimum bound, if that makes sense. Okay, so again, this is simply selecting the largest of all of these for the t near value, and then we're going to have t far, and likewise, that will be the minimum value, because, well, for the same reason. So let's say we have let's go 9.1 and 9.2. Well, if we select 9.2 as the furthest t value, which is still inside the box, well, guess what? The x-coordinate has left the box, so this is not accurate. So we need to restrict it. Given a bunch of maximum values, we need to always pick the smallest of those. We're getting the least upper bound, if that makes sense. So, how do we test whether our ray has hit? Well, there's a bunch of tests. First of all, the near value must be less than or equal to the far value. Secondly, if any of these is less than 0, then that part of the box is behind the viewer, if that makes sense. And it's fine for the near value to be less than 0. It's fine for some of the box to be behind our head. But if the far edge of the box is behind our head, that's a problem. It's not visible at all. So that's our second condition. Then we have one more condition, and that is that the near value must be less than the nearest hit which we've encountered so far. So if we have, what have I done here? This is just a whole, let's ignore all of that. Like I said, this function actually looks nothing like the sphere function. That's fine. It's actually quite a bit simpler. So again, if we've already hit a sphere at a distance of 5.3, then we don't care about any boxes which are further away from us at their closest point than 5.3. Does that make sense? Hopefully that makes sense. I always wonder, is what I'm saying making sense, or am I just going off the deep end? But anyway, so there we have it. That is our box function. Okay, so on to the main attraction, the traversal of the bounding volume hierarchy. This is going to happen in the trace function. I'm going to build it up one step at a time. So for now, yeah, we set everything up. Now we need to return a render state at the end that will store all of the color and all of the information for the next ray to be set up. So what we'll do is we'll just pretend that we're going through all of the nodes. In other words, no skipping at all. So there it goes. We're going through, we're looping through everything, in the end return the render state. Now, the important part is we need to know which node we're going to look at next. We're going to start this at 0. 0 is the root node. If, for instance, this has been set to 10, then we want to just keep skipping through the loop until we get to 10. Now, for that reason, it's super important how we set up the bounding volume hierarchy, the node tree, but I'll get to that in the construction stage. So what we'll do is we'll go node index doesn't match, then simply continue, and this will just run the for loop to the next stage. Okay, so if we get to this point, then we were searching for node number 10, we found node number 10, so let's start searching it. So first thing we're going to do is unpack that node. And then I want to know two things. Number one, is the ray going to hit the node? And secondly, is that node an external node or an internal node? Okay, so the external test is pretty straightforward. Do we have more than one ID and more than 0 IDs? Now, the way we're going to handle the hit case is, if we hit the node, then update the next node index. That will be equal to the node's hit link. And then, well, of course, if we didn't hit the node, then the next node index will be equal to that node's mislink. And as you can see, this is very elegant. We are by hand selecting the next node index that we want to search. So, if we hit this node, then we might go search node number 11 next. If we miss the node, we might go search node number 20. Okay, so we set that, then we just keep skipping through until we hit node 20 and then progress from there. Okay, now, on the other hand, if we hit the node and that node was external, I'll sort those brackets out in a second. That's annoying me, but we'll get there. Okay, so if we hit the node and it was external, then we want to work out the region that we're searching. Okay, so as you can, this is just, it makes things a little nicer, more visible. So we just start at the node offset and then we go to the offset plus the count. So for instance, if we are starting at node offset of 13 and we are tracking 5 spheres, then we're going to go from I equals 13, I less than 18, for instance. The next thing we'll need is we'll need to get the sphere index based on I. And then we can go ahead and search. So we search based on the sphere index that we just looked up, and everything else here will be the same. So we search and then do some stuff if we hit something. And there we have it. And hopefully there's no errors there. But as you can see, this is quite an elegant system. It's not bad. It's not bad. Anyway, full code in the description, but it's basically the same thing that I just went through. And that is it with the shader side of things. So we can go onto the Python side. Okay, so let's go back to our source code and we'll create a file to represent a node in our bounding volume hierarchy. I'll just go ahead and set this up with the usual. Now, this node won't be too exciting. It will pretty much just hold data, and we'll give it a bunch of default values. So there we have it. Yeah, so if we're in a tree, then we have a reference to the index of our left and right child. At the moment, we'll start them off with default values of -1, indicating that that has not been set. And the rest of these data fields should match what we've been working with so far. Min and max corner will be NumPy arrays, vec3s basically. So that's all good. Now we'll go more in depth in this when we come to actually create the BVH. But at the moment, let's just concern ourselves with the data. So we've got this, but I also want to go to the app. And in the app, I'm going to create a list to track all of the sphere IDs. Actually, a few of these. So we'll go sphere IDs. Oh, I'm making this in the wrong thing. Not the app, the scene. Okay. So essentially what this is saying is we have, 1,024 spheres, and we're setting up a what am I thinking? A lookup table, which at the moment is going from 0 to 1,023. We may be changing those in future. And just remember, I think I forgot to mention this, but we are importing Node in our scene. So this is basically pre-populating the nodes, but all of the tests will be based around the number of nodes which have actually been used. This 2 times sphere count +1, I think it should be -1. It's fine. That's fine. We'll pre-allocate more space. Has to do with the fact that theoretically, if we took everything down to its lowest level, then if we had 1,024 spheres, we'd have, I think it's double that. -1 is including the internal nodes and external. We're not going to use all of that, but anyway. So we'll go over to the engine, and I'll just write some functions to allocate this space and write the data to memory. So we'll go to create resource memory. And yeah, so as you can see here, this is creating the spheres. Now if we go over to the ray tracer and go down to the node information, then here we can see that every node is going to use 3 pixels, which is 12 floats. So we can duplicate this code down here. We'll go call this array node data. That is probably fine. Yeah, we can generate one texture. And that is texture number 2. Okay. Just double checking that. That all looks fine. And then we're going to go down here. We're going to have 3 pixels across, 1024 deep, based on node data. Okay, great. Then we'll grab that same code again and we'll use it for the sphere lookup. So yeah, as you can see, we're going to use 4 floats. Yeah, 4 floats. Sphere lookup data, sphere lookup texture. That will be texture number 3. It's a lot of fun here. We're just going through the motions really for this bit. We got 1 float across and yeah. Okay. I think that's looking fine. So that has allocated all of the space for the underlying arrays as well as the textures that will get that data. Okay, that's fine. Then if we go down here, we have this record sphere, and we're just going to make, and again, 2 copies of that. We're going to have record node and record sphere index. Yeah, no, it's very, I don't know. It's a lot of typing, but that's fine. Now, I just noticed something, and this is, I'm literally just experimenting with this. Let's go. So the thing that I'm wondering, and this might be a complete, like I might abandon this completely, but I'm just on the spot at the moment. If I have this node, as you can see, that's white, so it's not recognizing the attributes of it. But if I specify that that is a node class, then hopefully, oh yeah, then I can read the data. Huh, that's cool. That is very cool. Okay, so let's go with that. See, it's blue, it's reading it. And I can actually do that up here as well. And now it's understanding that as well. Okay, that is, I'm over the moon with that actually. That's really cool. But anyway, so our stride here is 12. So just keep on keeping on. Oh, and we shouldn't be writing to object data. We should be writing to node data. Okay. Oh, and I just noticed always something. Good thing I spotted it. Okay, very cool. So now let's go here and record sphere index. We have a stride of 4, and that's literally it. We'll just write in the index. There we have it. Okay, cool. So we've got those data writing functions in there. Okay, now we have update scene. We're going to have to, we're going to have to send some things. So we'll go here. I'm just looking through this again. Yep, that's all looking good. So that's writing the sphere data. Oh, this is cool. Okay, let's try this. Let's go import scene. I'm just having a ball today. Okay, so update scene, but we know that that is an instance of scene. And then if we look here, it now recognizes that this is a list of spheres. Okay, very cool. I'm always learning new things about Python.
this isn't, I already knew this, but this is just, it's fun to see it in action. Okay, so node count, and we want to write in the number of nodes used. And then we'll just loop through. Actually, I'll do this. So I found out there was something, it was a weird check, maybe something I should have a look at in the future. But for some reason, in some cases, I was getting the minimum corner being none. So we'll just, as a security check that it's not none. And in that case, we'll go ahead and record it. Okay, I think that's fine. All right, so we have written all the node data into the flattened array, and then we've sent that flattened array to the node texture. Okay. So now what we can do is we can look through the sphere lookup data, through the sphere IDs, and then record those sphere indexes. Oh, why did I? Oh, yeah. Okay, record sphere index. Okay, no problem at all. And just double check that I'm writing to the right thing. Yes, sphere lookup data. Okay, cool. Okay, fingers crossed. And again, hey, we'll find out sooner or later. So we can go back, and then when we prepare the scene, that is all looking fine. We'll just need to send over that data again. So I'll go to texture 2, and texture 2 is going to be the node data texture, and then texture 3 is going to be the sphere lookup texture. Okay, excellent. Repeat myself a lot. Excellent, excellent. All right, so we've got that. But the rest of this should be fine. Yeah. That's fine. Because we're just reading all the data. Okay, I'm talking to myself. That's fine. So the next thing I'm going to do is going to look at the BVH construction. But before I do that, I want to have a look at quicksort, an in-place quicksort. It's a cool technique for ordering partitions of arrays. All right, so here we are. In-place quicksort. I wanted to do this by example, have a bit of fun. So let's say we have an array of 16 numbers going from 0 to 15, and I couldn't find a regular die, so I've got this D3, I guess. Beggars can't be choosers. And let's just roll a bunch. I don't know why that last total took me so long to calculate, but okay, we have a bunch of numbers between 0 and 8. I guess halfway between 0 and 8 is 4. So let's say we want to go with a pivot of 4, which means what we want to do is organize the list so that after we've run this loop on it, the first portion, everything will be less than 4. The second portion, everything will be
greater than or equal to 4, for instance. Now, the way this works is we track two variables, being the start and end position of the list. So we'll go I is the start of the list, J is the end of the list, which is position number 15. Now, what we do is we step across, we look at position I. So position 0 has the number 5 in there. 5 is not less than the pivot, and so we will swap it with the J position. So we go ahead, we swap this, and now we know that the thing in position 15 is greater than or equal to the pivot, so we don't need to consider that, and we'll bring the J position, the end position, forwards by 1. Now I look at I, it wasn't a good swap, we got 6, so we're going to have to swap again. So we look at, yep, okay, swap that with this thing here. And then again, this element is greater than or equal to the pivot, so J decreases. Now we look at I again. Oh no! Well, I guess we decided that we want the left bit to be less than or equal, so we're going to have to swap again, unfortunately. But now we actually have a good swap. Now we've got something in the Jth position, which is actually less than the pivot. Ith position, I mean. So when we look in position I, position 0, that is less than the pivot, so we're happy with that. So then we say, okay, happy with that. Bring I forward by 1. Look in the first position, position 1. Oh no, we're going to have to swap. But that means that we now know position 12 is okay. We look at so then we've done a whole bunch of swapping, but finally we get a 3 here, which is good. Then we look at position 2, and position 2 is less than or equal to our, less than our pivot. So that's good. We look at position 3, we are good. We look at position 4, we're going to have to swap. I may have missed that. Yeah, whoops, I forgot to decrement that once. Anyway. Yeah, so again, we look at position 4. Position 4 is now good. And we look at position 5. I'm going to have to swap it. And then finally, you can see where this is going. We look at position 5. Position 5 is good. We look at position 6. Not so good. So swap it. Whoops, what am I thinking? Okay, so then look, we've ended up with a situation where now the I position matches the J position. In other words, we started at the front and the back, then we came towards the center, and that can be our stopping condition. Now, the efficiency of this depends on how good the pivot was and how nicely ordered the data was, but in general, it's about n log n, I believe. Anyway, so there we have it. That is quicksort, and this in-place quicksort is what we're going to use. It's what we're going to use to order the objects in our scene, because we start out with our sphere indices, and then depending on some various subdivision tests, we're going to reorder them, if that makes sense. Okay, so let's jump into the code now. We're on the home stretch now. Let's head to the scene, and we'll go ahead and construct everything. Okay, so this is going to go in 2 stages. First of all, we're going to build the bounding volume hierarchy, and then we're going to build the links. We're going to have to start that at index 0 being the root. Now, the bounding volume hierarchy will construct a regular linked list style tree. Left child, right child, internal node, external node. the build links is going to populate the hit and miss links for each entry, so that we then have a structure that we can pass on to the GPU and it'll work with that. So let me just give myself some space. Okay, so using my newfound notation, why not? So here we'll set the first sphere index to 0 and the sphere count to basically all of the spheres. Now, just a note, if I get rid of this, then as you can see here, Python really doesn't know what variable type this is. So including that, it understands, it just makes it easier to debug. Additionally, even though we have a default value of 0, let's set that value anyway, why not? And increase the number of used nodes by 1. Okay, so we've got that. Now basically what this is doing is this is creating the root node for the bounding volume hierarchy. What we'll then do is we will update the bounds for that bounding volume hierarchy. At the moment it has a default min and max corner of nothing. So updating the bounds will expand the corners in order to capture all of the spheres inside it, and then we'll subdivide that space. So again, we'll update the bounds for thing number 0, and then subdivide thing number 0. And this looks weird because we haven't written those functions yet. Let's write them now. Okay, so to update the bounds, first of all, we'll fetch the corresponding node. Now, I know this might seem a little strange at the moment, but we are going to be using this type of 111 array quite a lot in this function. So what I want to do is I want to give this a minimum corner which is unrealistically big, and then I'm going to shrink it according to each of the spheres. So I'll go with that one, and then for the maximum corner, again, I want something unrealistically small, which will definitely have to grow for each of the spheres that we add. Now this might seem a little strange that I'm capturing, I'll go through this and then you'll see what I mean. So if we go for I in range again, this might seem a little strange, but as more things get subdivided and the sphere indices get messed up a little bit more, we want to keep track of the nodes. They might have different starting points, if that makes sense. So long story short, what this is doing is this is capturing all of the spheres which are owned by each node currently. So this is where things start to get strange. So we want to find the extent of the sphere. In other words, its minimum corner and its maximum corner. Now, of course, its minimum x would be its x center position minus its radius in the x direction, minus its radius times 1. But if I use this helpful array, then we are adding or subtracting all of the dimensions in one go, which there's no reason not to do that. It works just fine. It's pretty elegant. So what we can do is we can go, okay, take the node, and its minimum corner is going to be the minimum of its current minimum corner and the sphere's, whoops, the sphere's minimum corner, if that makes sense. And if we check this, it says this is the element-wise minimum of array elements. So when we throw in the first sphere, of course, whatever number we have here has to be less than 1 times 10 to the 30. So the x, y, z of the minimum will simply be the x, y, z of the sphere. And then as we throw in the next sphere, some of those dimensions might be less than the current extent, and then the extent would update, but it will just update based on the specific dimensions. So in other words, long story short, I know I have a tendency to ramble. The point is this bounding box starts at unrealistic dimensions and then shrinks, what could I say? Shrinks or grows tightly around the spheres which have been thrown into it, if that makes sense. Okay, so I'm pretty happy with that, and that's all we need to do for this update bounds. By the end of this loop, the minimum corner and maximum corner will be appropriately set so that it has tightly grabbed all of the spheres, or tightly on the edges, maybe not so tightly on the inside. So the next part is the subdivide function. Now the way this is going to work is we'll grab a node and then we'll take the extent of the node, which is the difference between its minimum and maximum corner, and then we'll try to split that extent into two pieces, and then we'll work out which spheres are in the left piece and which spheres are in the right piece. What I'm doing here is I'm putting an early exit test. I found, well, I mean, ideally we might want to just divide this down to the point of having 1 or 2 spheres, but the problem is if we choose a small maximum sphere count for each box, then the cost of testing the rays against the boxes starts to stack up with the number of boxes. So just for my performance, I found that about 16 spheres per box was a good, I could rejig that maybe. I think 8 or 16 is about the optimum. So what we're doing here is we are looking at which axis to split along. Is it X, Y, Z? And the criteria that I'm using there is just whichever dimension of extent, the difference there is larger. So I guess first time maybe we'll split on the X, and then the next time we'll split in the Y, and so on. And this works pretty well because the spheres are uniformly distributed. And now this split position is the position along that axis. Like say axis equals 0, we're splitting along the x-axis, and then we find that the midpoint along there is about 7.5. So then everything with an x of less than 7.5 would be in the left box. Everything with an x of larger than 7.5 would be in the right box. That's as simple as it is. So now we'll go ahead and we will partition into 2 halves. Now, remember the in-place quicksort that I did before. We're going to go with that. So we'll say position I will be our node's first sphere index, and then position J will be the end of that partition. So it'll be the first index plus the node's sphere count minus 1. That's the end there. Then we'll keep looking through here until our I and j run into each other. Okay, so if we pass the test, if our x value of our center is less than 7.5, okay, fair enough, we do nothing. We just increase the I position. Otherwise, we'll have to swap this, the thing in the I position, with the thing in the j position. So we'll go through that swap. Okay, cool. So remember, for each node will control a region of the sphere IDs, and we just swap the sphere IDs at those positions. And so after this loop runs, that region of the sphere IDs will be ordered according to this split. And it's fine if that region is then subdivided, because the subdivision on those subdivisions and so on and so forth will be reordering the sphere IDs, and everything will be just fine. Okay, so now what we need to do is we need to work out how many things were in the left and right. Yeah, how many things are in the left and right portions? So because I started at the left child index, the first child index, sorry, and kept increasing, then the difference there will be the number of spheres in the left subdivision. So this is just an extra check we can put here. So if the number of things in the left is 0, in other words, nothing got thrown into the left, it was a pretty dodgy partition, or if the left count is equal to the node sphere count. In other words, if nothing got thrown into the left box, or if everything got thrown into the left box, that's a pretty bad partition. We can simply return and don't subdivide. We've probably got an optimal split already. Okay, so we're just setting up the data for the left child. We tell the node that where its left child is. Okay, I'll quit with the running commentary. Okay, so we're setting up the left node. Now, bear in mind, pay attention here. This is important. Remember, the left part of the partition has everything less than the split position. So we know that the left node is going to hold the spheres from the first index and have left count of those. We already calculated that up above. Now, also note that we then immediately update and subdivide the left child before looking at the right child. Now, the reason for that is that this tree needs to be, its default order needs to be depth first search. We can't have it so that the right child is just one more than the left child. That's what would happen if we were setting the left and right children and then updating and subdividing both of them. The issue with that is that it would, okay, so let's say we go and search the left child, and the left child is a much higher number than the right child. Well, because of the way that for loop goes, it doesn't work unless this thing is in depth first order, because then if we want to go on to the right child, well, guess what? That for loop that we had here, where are we? In the trace, if the left child is thing number 11, the right child is thing number 12, but then the left child's children go down to much higher numbers and we search some of them, but then we want to go back to thing number 12, this for loop is non-decreasing. It's monotone increasing, basically. So that's not going to work. Long story short. Now I'll just go and update all of this. We're going to go okay, so up here, the beginning of the right children is, oh, that's not right, is it? There we go. The beginning of the right children is at position I. That's the middle of the list after doing the quicksort. Now, the number of things will be the nodes sphere count minus the number of spheres which went into the left. I hope that makes sense. Then we set that up. And then the last thing, this is super important, is working on the current node. We need to set its sphere count to 0, and this marks it as an internal node. Okay, so hopefully I didn't mess that up too much. I'll just quickly check through it. Yeah, I think that's fine. We'll find out sooner or later. So we'll just cut that down. Oh. And now I need to make 2 more functions. We are so close to done on this. And then we'll go on to error checking. But what we'll do is I'm going to make a function called getRightChild, and this will be used in building the links. So we need to know 2 things. We need to know which parent is the right child being requested of, and which node is doing the requesting. Remember, when we build these things, we sometimes want to know what is the right child of our parent. And the way this goes is if a node's right child is requesting your right child, then you recursively go and ask your parent for their right child, and that continues. But then if your parent doesn't exist, then you just return -1, and that indicates a terminal state on the traversal. But anyway. Okay, so because of the non-decreasing nature of the children, the right child will always be a higher number than left child. So we can quickly check if it's the right child requesting this by checking if the parent's left child is less than the requester. In this case, we'll also check if we don't have a parent. Return -1 in that case. Otherwise, return recursively. So in other words, we are now requesting it of the parents. What does this mean? We're now requesting it of our parent, and we are the thing requesting it. Anyway. All right. But if none of that gets set off, then we have a legitimate case where we simply return the parent's right child. Okay, now finally, last function. Okay, now I'll just go through the usual. Okay, so the goal of this function is to work out the hit and miss links for each node. So the first thing we'll do is we'll try to work out the hit link. Now we want to check, is this node internal or external? It'll be internal if its sphere count is 0. And because of the way this works, if we've got a sphere count of 0, then when the thing gets hit, we want to search the left child first. Otherwise, I'm just looking through my notes here. So I've got something external. Okay, so let's say we just have an external node, but for whatever reason, yeah, okay. I've just zoned out for a second. So let's say we have an external node, but it doesn't have a parent for whatever reason. Say, for instance, we're just running the scene with 1 or 2 spheres, so there's no reason to really subdivide it, and we just have a single thing. Now, if we hit that thing, that's it. Nothing else. So in other words, what we're saying is, if the node's parent index is less than 0, then don't even bother with it. Okay, so otherwise, if we're on an external node and it has been hit, we then want to check our right child. Okay, so that is the hit link. Now the miss link. So yeah, very simple. Typically the miss link is always the parent's right child, and that runs recursively, so we can run several steps up the tree, and we simply put a check beforehand. If our parent doesn't exist, then I guess the miss link is just going to fail completely. Okay. In other words, if we're on the root node and we fail the root node, well, geez, we can't hit anything. That's fine. Anyway, so where was I? We then want to recursively build the links on everything else, but we just want to check if we have children. And a quick way we can check that is if our left child exists, basically, isn't -1. Okay, and that is it. It's been quite a journey, but try to take it at a conversational pace, and here we are. So again, we set everything up. We have our sphere IDs, which are then jumbled around by the various partitions and subdivisions. And then we have our nodes. Okay, great. We start off with using 0 nodes, and then we build everything. So in theory, it should be working. I highly doubt it'll work. It's probably some boneheaded blunder I've done, but let's give it a go. Yeah, absolutely. Okay, what have I done? 188. Okay. Just give me a second here, folks. Oh yeah, what is this? Vec? How did I miss that? Let's just test that. It seems to be indicating that extent is an integer, which it shouldn't be. It absolutely is not. It's an array. So what's going on? Oh, jeez, what's going on here? Okay, so that should be axis, not extent. Again, another, how did I miss that moment? But that's live coding for you. Okay, 246. Yes, that should be length. Okay, so it's saying, yeah, okay, so engine
246. Are you enjoying this? Just let me know if you're enjoying this. Okay. And it shouldn't even be length, should it? It should be... And there we go. Okay, so just give it a second to up-res, and then we'll compare the resolutions. Remember, it's adapting the resolution automatically to keep a frame rate of 60 frames per second, and so the difference should be in the higher resolution. So there we have it. Performance is a little lower because we're running OBS, but as it was for the first trial anyway, so I don't know, I'll put the other footage up compared to this, and hopefully you should be able to see a difference. I've definitely seen a difference in my own tests. Now, where the real difference is in cases like this. So if I look here, you can see that our frame rate popped up. If we look back, suddenly it drops down. So it is dynamically adjusting the frame rate depending on where those rays are going to hit, compared to the brute force method, in which rays on the right of the screen would be testing every single sphere over here. So anyway, I mean, personally, I think if you're going to make a ray trace game of any sort, we need to have some sort of acceleration structure, and being able to run it on the GPU is a massive benefit. Anyway, hope you had fun. I know this was a bit of a long session, but anyway, hopefully I explained it well. And yeah, all the best. Hope to see you again soon, and have a good one. Bye.